For 53 years, we walked away from the moon, like a childhood home we thought we'd outgrown. But in 2025, everything shifts, not gradually, dramatically. 3 convergent missions, 2 commercial landers per quarter, 1 crewed flyby that breaks half a century of silence. And at that exact moment, the machinery doesn't just resume, it accelerates. Artemis II is stacked and tracking toward a 2026 crewed lunar flyby. At the same time, commercial landers are being integrated with instruments to hunt resources we've never extracted off-world. Water ice, regolith chemistry, radiation mapping, seismic activity. The machinery is humming. The logistics are real. But here's the truth. Almost no one frames clearly. 2025 isn't about going back. It's about learning how to stay. It's not sending explorers. We're sending infrastructure, machines first, humans second. The order matters. 3 questions define this moment. What makes this moment different from 50 years ago? Can private companies actually reshape humanity's space future? And what happens when we confirm the moon can support a permanent presence? It's as if the cosmos held its breath, and 2025 is the exhale. According to NASA's 2025 Artemis Baseline Mission Design Review, released Q3 2024, the first crewed flight of NASA's Artemis program will perform a lunar flyby aboard the Orion spacecraft, powered by the Space Launch System, generating 8.8 million pounds of thrust at ignition. That's 120% of Saturn V capability. This isn't hyperbole. The SLS stands 322 feet tall, taller than the Statue of Liberty. It concentrates more than 8.8 million pounds of force at a single point in time. Flight duration, approximately 10 days end-to-end. The crew will spend that time validating SLS and Orion's life support systems, navigation, communications, in deep space. This is the full-dress rehearsal before the surface campaign that follows. Orion will reach speeds of 39,000 kilometers per hour at trans-lunar injection. This isn't a quick hop. This is a systems validation mission on a scale that hasn't been attempted since 1972. Why this matters? Crew systems validated around the moon reduce risk for the next steps, boots on the surface, extended stays, logistics chains that don't snap under stress. NASA's CLPS initiative distributes approximately $2.6 billion across 5 primary contractors: Intuitive Machines, Astrobotic, Firefly Aerospace, Maston Space Systems, Sierra Space. Each team receives fixed-price contracts for multiple landing attempts, not one mission, but a cadence. Here's the fundamental shift. Instead of NASA building and launching a single flagship lander every 5 years, CLPS creates a marketplace where 5 companies race to demonstrate capability in parallel. In 2024 and 2025 alone, Intuitive Machines logged 2 attempted missions. By 2027, commercial landers will have made 15 or more attempts at the lunar surface, iterating and learning at a velocity NASA alone could never achieve. Each payload carries a purpose: cameras for site reconnaissance, resource prospectors mapping chemical composition, radiation monitors characterizing hazards astronauts will face, and in some cases, seismometers, hardware that maps subsurface voids we've never detected before. Firefly's Blue Ghost program and Intuitive Machines flights aren't tourism. They're targeted capability building. The cadence shift is everything. When a payload fails, we learn quickly. When it works, we bake it into the stack for the next mission. In traditional government spaceflight, a single failure can delay entire programs by years. In CLPS, a single failure teaches and accelerates. Water ice at the lunar South Pole remains incompletely mapped. Radar observations from the Lunar Reconnaissance Orbiter suggest deposits ranging from 100 million to 1 billion metric tons across all permanently shadowed regions, a spread of 10 times. Why the variance? Because we haven't deployed prospecting instruments at scale. That's exactly what CLPS missions will do in 2025 and 2026. Narrow that uncertainty band through direct sampling and in situ measurement, Permanently shadowed regions exist in craters near both lunar poles where sunlight never reaches. Temperatures drop below -170 degrees Celsius. In this cold trap, volatile compounds, including water ice, accumulate and remain frozen across billions of years. Ice doesn't just mean water, it means three things in one: life support, drinking, oxygen generation, radiation shielding, masses to block cosmic rays and solar particle events, and propellant, split into hydrogen and oxygen for rocket fuel. If we can extract and process lunar ice economically, the moon transforms from a dead-end destination into a depot, a refueling station for missions deeper into the solar system. The entire calculus of space exploration changes. The first two Gateway modules, PPE and Halo, are planned to launch together on a Falcon Heavy no earlier than 2027. Gateway won't be a hotel, it's a utility, a logistics node, staging point, communications relay, and science lab in a near rectilinear halo orbit at 70,000 kilometers altitude with a 7-day orbital period. This orbit is mathematically elegant. Instead of orbiting directly around the moon, Gateway sits at a gravitational balance point, the NRHO, where Earth's and Moon's gravity nearly cancel. This means Gateway needs minimal fuel to maintain position, allowing it to stay operational for years. More importantly, it functions as a repeatable rendezvous point. Crews launch from Earth, reach Gateway, transfer to a descent vehicle, land on the moon, return to Gateway, and then coast back to Earth. It's a transportation node that de-risks surface cadence by making each leg of the journey predictable and testable. NASA and mission partners prioritize sequence and adjustment and redundancy. This isn't because government agencies are slow. It's because government uncrewed missions tolerate approximately 10% failure rates. Government crewed missions tolerate less than 1%. The margin is non-negotiable. Here's how it actually works. Artemis II validates life support and navigation in deep space, reducing unknowns before landing. Artemis III, no earlier than 2027 or 2028, executes a short-duration surface mission, 7 to 10 days maximum. Only after Artemis III succeeds does Gateway support sustained operations. Multiple sorties per year instead of one? Why this order? Because each step informs the next. Thermal data from Artemis II. Crew systems, how much heat the Orion capsule generates, how efficiently its radiators shed heat, how crew comfort systems perform over 10 days, becomes the engineering baseline for pressure suit design. Artemis III. Third surface discoveries direct where Gateway infrastructure gets positioned and how surface habitats will be protected. Regolith electrostatics. Static charge buildup in lunar dust. Dust abrasion rates. How quickly suit material degrades. Thermal cycling damage. Material brittleness from extreme temperature swings. Its cumulative risk retirement. Each mission removes categories of uncertainty, so the next mission can push further into operational territory. Private teams operate at different margins. SpaceX went from Falcon 1 in 2006, which failed, to regular orbital flights in 6 years through rapid iteration. Relativity Space is 3D printing rockets at scale. Blue Origin's Blue Moon lander evolved through 12 design iterations in 18 months. Under commercial logic, why wait for Artemis III to land when private landers can already be surveying sites, testing power systems, and validating communications? The honest trade-off: commercial risk tolerance for uncrewed missions is 30 to 40%. Acceptable loss rate considered normal. Government uncrewed is approximately 10%. Crewed is less than 1%. They operate at different margins because the stakes are different. A failed SpaceX cargo mission is recoverable. A failed commercial lunar lander teaches expensive lessons, but a failed crewed lunar mission costs lives. This is not weakness in private industry. It's a feature. Commercial companies accept higher losses on uncrewed payloads because the learning velocity justifies it. Government can't accept those losses on crewed missions because there's no learning if the crew doesn't come home. The genius of CLPS is that it recognizes this trade-off explicitly. Let private companies iterate at 30 to 40% loss rates on uncrewed technology. NASA harvests the successful iterations and uses government risk tolerance, the less than 1% standard, for crewed missions. Both systems working in parallel, each optimized for its constraints. This isn't NASA versus private, it's NASA plus private. Synchronized. Take relay communications as the real example. Intuitive Machines' Lunar Gateway Relays, LGRE, are privately built but integrated into NASA's Deep Space Network protocols. Commercial landers transmit data through these relays. NASA Mission Control receives it on the same data streams as government satellites. Same spectrum, same standards. One unified network, multiple vendors. This is the 2025 story, not dominance, but interoperability at scale. When it works, private speed feeds government safety. When it breaks, both sides have incentive to fix it fast, because interdependency is real. The calendar inversion reveals the sophistication. By the time Artemis II Spanner's crew flies in 2026, multiple commercial instruments will already be operating on the surface. Machines first, humans next. That's a profound narrative inversion compared to Apollo, and it's exactly the engineering point. Humans don't scout anymore. They arrive at places that are already characterized, with infrastructure already deployed, with hazards already mapped. Within 3 years, the lunar South Pole stops being a vague there and becomes a place, not mythology, infrastructure. This transformation mirrors how Antarctica shifted historical perception. For centuries, Antarctica was the bottom of the world, abstract, mythological, the unknown South. Then came Shackleton's expedition and systematic survey. Suddenly, Antarctica became the South Pole Station, the Ross Ice Shelf, the Trans-Antarctic Mountains, named, mapped, real. The lunar South Pole will undergo the same transformation, named craters, lighting maps coordinated at 3-degree accuracy, relay orbits with deconfliction zones, specific orbital paths where multiple landers won't collide, traverse routes marked by hazard flags, site-specific data architecture. This ridge is ice-rich but thermally unstable due to subsurface void spaces. That crater floor holds water but enters 60-day darkness cycles where power systems must sustain on battery alone. The transformation is epistemological. We move from mythology to infrastructure, from out there to here's the operations manual. As operations expand, the moon transitions from exploration target to economic territory, and legal fault lines crack immediately. The 1967 Outer Space Treaty bans national sovereignty over celestial bodies, but it says nothing about corporate claims. The Artemis Accords, signed by 27-plus nations including the United States, Japan, Canada, ESA members, Australia, and others, outline principles: transparency, interoperability, deconfliction, resource utilization consistent with international law. But Russia and China aren't signatories. They're building competing frameworks. They have their own lunar programs, with their own timeline ambitions. In 2025 and 2026, expect the first disputes. Who owns the water ice mined by a U.S. company from a crater claimed by China? If a Firefly lander lands in a zone pre-claimed by Artemis Accord nations, does commercial have legal right to extract? If Intuitive Machines establishes a relay station, can Russian landers use its communications network without permission? These aren't abstract debates about international law. They're property rights disputes worth billions, playing out in real time as robots cross invisible borders on a world that has no border control. The regulations don't exist yet. We're writing them as we go. When those 4 astronauts arc around the moon, the first humans to see it with their own eyes in 53 years, they won't be scouting a blank slate. They'll be arriving at a place that's already home to machines. Through their cabin window, radio beacons pulsing, relay antennas glinting in distant sunlight, camera feeds streaming live data from landers below them, seismometer data rendering subsurface maps in real time. They won't be discovering the moon. They'll be connecting to it. The emotional weight shifts. It's not, we were first. That's Apollo's frame. It's we're arriving at a place that's ready for us. They're not explorers in the romantic sense. They're operators conducting inspections of infrastructure humanity deployed remotely. This reframe changes everything about how we narrate human spaceflight. We're not conquering new frontiers, we're establishing permanent presence through logistics networks. It's less romantic, it's more real. The data streams of 2025 and 2026 don't close the scientific book, they rewrite it. When seismometers deploy at the South Pole, they'll map the moon's interior. But what if they detect subsurface caverns? What if the seismic signatures suggest water ice isn't uniformly distributed, but concentrated in geologically recent impacts? What if the radiation environment is higher than predicted, not globally, but concentrated in solar wind shadow zones? Consider the ice trapping mechanism debate currently unresolved among lunar scientists. Some researchers argue permanently shadowed regions trap volatiles through cold trapping. Ice simply accumulates and stays frozen across geological time. Others propose subsurface ice-rock interactions create thermal insulation that locks water deeper than surface models predict. Both theories predict ice at the poles. Neither fully explains the distribution pattern observed by Lunar Reconnaissance Orbiter radar. CLPS missions will deploy spectroscopic samplers and drilling instruments in 2025 and 2026 to resolve this. The answer changes how we plan extraction infrastructure. Different deposit geometries require different mining approaches. That's the real possibility. Not that we'll confirm what we already believe, but that the data will surprise us in ways that force us to reimagine the moon's geology, its resource accessibility, and the timeline for sustainable operations. We've journeyed from mechanical thunder to logistics choreography. The facts reveal an unprecedented mobilization of technology and resources aimed at our celestial neighbor. The theories expose competing visions: government sequence, commercial speed, hybrid integration, colliding and recombining. The possibilities suggest we stand at a threshold where systematic discovery meets industrial infrastructure. Why 2025? Because it's the year the chain aligns. Commercial robots pioneer and de-risk the high uncertainty elements. Artemis II in 2026 proves human flight systems in deep space. Gateway, no earlier than 2027, begins to industrialize cadence. We're leaving the government or private narrative and entering the hybrid system era. Distributed, iterative, interoperable. What we know: NASA's official roadmap shows a steady progression from Artemis II's orbital flyby through surface landings and eventually towards sustained gateway operations. Robotic missions throughout 2025 and 2026 will characterize an environment we abandoned 53 years ago. Private companies are reshaping how space exploration works by making it economically viable. The data streams are real. The timelines are locked. What's emerging? A new model of human expansion. Not the old binary of government-led or private-led exploration, but a hybrid system where both operate in integrated chains. Not conquest, but something more complex and uncertain. Systematic occupation built on distributed infrastructure. Here's the question that matters, though. When sustained lunar operations begin, and data streams back in unprecedented volume, will we discover something about the moon that fundamentally changes why we need to be there? Water ice is the obvious thesis. But what if seismic data reveals subsurface caverns that suggest the moon is geologically more active than predicted? What if regolith chemistry reveals rare elements and concentrations that alter the economics of extraction? What if radiation shielding requirements prove higher or lower than models suggest, forcing us to redesign habitat architecture entirely? The datasets of 2025 and 2026 don't close narratives. They rewrite them. The moon's silence has been our loudest teacher. For 53 years, we asked no questions because we sent no instruments. In 2025, we finally learned to listen, and we start moving in for the long term. The next launch window can change everything. Instruments are powering on right now. Schedules are locking. Data is coming home. Here's what's coming. Intuitive Machines IM-2 mission targets Q4 2025. Astrobotic's Griffin Mission 1 targets early 2026. Artemis II launch window opens March 2026. Each launch is a data point. Each dataset rewrites the operational roadmap. Miss these moments and you're watching history through a delay. Subscribe if you want to follow this in real time. Be the first to know when commercial landers reach the surface. Follow the data streams from seismometers and radiation detectors as they paint a new map of the lunar environment. Join the conversation about how we make a lasting, responsible presence beyond Earth, scientifically, economically, ethically. The question isn't whether we'll return to the moon, it's whether you'll understand how, in cosmos, we trust.